Hello, today we'll see sheaves, we'll see the definition, and we'll see some examples and some non-examples. And yeah, that's the plan for today. So let's start with the definition of a presheath. So let's take a topological space and we define a category C. So and this consists of the following objects, namely, as objects we have the open sets of X, and as morphisms we have inclusion morphisms. So we have a morphism from, say, inclusion, or we can also say the subset relation. So we have a morphism from U to V if and only if U is a subset of V, or if we have an inclusion map. Okay, alternatively we can also consider another category. Well, that's quite similar, but let me just give you some more generality. So we consider any poset that is a partially ordered set, and we see this as a category with objects are just the elements from the poset, and morphisms, so we have exactly a morphism from X to Y, and then if we have one it's unique, and if and only if X is less than or equal to Y. Okay, but we won't deal with posets any further, but just to give you some more generality. Okay, and now let's define a presheath. So a presheath, let's say, of abelian groups. We can think of other stuff, but let's start with abelian groups. On X is just a contravariant functor from C to the category of abelian groups. So that's a nice and short definition, but let me tell you what this means. So we could alternatively think of the category of sets, or rings or other categories, and then it would be a sheaf of rings or something like that. Okay, let's see what this means. So we have for all open sets we have a abelian group or set or whatever, f of u, and we have morphisms between them. Namely, we have for all subsets, so all these subsets are open, we have a map from f of u to f of v, because this functor is contravariant, so it reverses arrows, and we call this a restriction. We'll see later why we call it restriction, or we might just write the restriction symbol or the restriction symbol with saying what we restrict to, in this case v. And so we have this morphism, and this morphism has certain properties, namely that for if we have W subset V subset U subset X open, Then we have f of u, f of w, f of v, and then an arrow here, and this commutes, and from f of u to f of u we just have the identity. So all this stuff here, so that's a lot of information, and it's basically all included in this being a contravariant functor. So that's nice because we don't have to remember these diagrams, we just need to know that's a functor. Okay, so now let's look at some examples. So let's put, for example, x to be r, or you can think of r to the d. So for the examples it doesn't really matter, but of some real space or some, so x is some real space, and then so we have, let's define the first sheaf, namely the functions from u to r, so just real valued functions, and with the usual restriction of functions, and all these examples I give will now be with the restriction of functions. So then we have functions, so the continuous functions from u to the reals. We can so a presheath f, so yeah, I already wrote it here, so that's f. Okay, and then we could also think of differentiable functions, or let's give a final example. Let's take constant functions. Okay, and let's see, in all these cases we can just restrict the function to subsets, and well, function restriction obviously has these properties. So if we restrict a function f of u, it's the identity, and if we restrict it twice, it's the same as restricting once. So restricting over two subsets, so over this path, is the same as over this, and so that's all fine. And I'll tell you later why I choose this many examples, because later we'll look at. So now I'll define what a sheaf is, and then we'll see which of these examples are sheaves. Okay, so let's define a sheaf. So again, as before, X is a topological space, and a sheaf on X is a presheath that satisfies the following two conditions. So the first one is that let's take a U to be an open set, and let's take an open cover. So we have an open cover, and now let's take f and g in f of u. So this, you can think of them in these examples as functions, but it doesn't have to be a function. And now the condition is that if f restricted to ui is equal to g restricted to ui for all I in the index set, then f is equal to g. Okay, that's the first part of the conditions. And the second condition is we take again an open cover of an open set U, and now let's take fi's. So here we took two elements from f of u, but now we take elements from f of ui, and they should have the condition that if we restrict fi to uj, that, or well, ui intersection uj rather, and fj to ui intersection uj, then they are equal. So we want this for ij in I, and so we have this, and the condition is now that if we have such elements, then there exists an element f in f of u with f restricted to ui is just this fi, and again for all I, and you can think of this as gluing, and also this f is unique by 1 if 1 is satisfied. Okay, so let's see what this means. So basically it means, if we think of functions, it means that if we look at them locally and they are locally equal, they are also globally equal. And here it means if we have functions that agree on the intersection, then we can glue them together to get a function on the whole space or whole open set U. Okay, that's the definition and what we think of it. And now let's look which of these examples are sheaves. Okay, let's look at the real valued functions. So if they are locally equal, then they are definitely equal. And or let's maybe first check this first condition for all 4 examples. So also, if the continuous functions are locally equal, they are globally equal, and the same holds for differentiable and constant functions. So now let's check part 2 for all these presheaves. And so let's see. So if we have functions that agree, just arbitrary functions, so here in 1 we have arbitrary functions, and if they agree on the intersection, then we can just define the function, a function on the whole space, and we are fine. So this gives us a sheaf. So that's a sheaf. So as we said, 1 is always satisfied, and now we look for 2. Then we can also check continuity locally. So what this means, so we could always, so for as in f1, we can define a function that agrees with these with the local functions. So with local I mean with the functions in here, and with global I always mean this U. So we can look at them. We can define a global function and it's still continuous because we can check continuity locally. The same holds for differentiable functions, so we can define it and we can we get that it's again differentiable. But now for the last one, we could still define a function, but it would be just a function and it wouldn't have to be constant. So what I mean is that let's say we have the real line and we take two intervals, say u1 and u2, and the elements from u1 get mapped to 1 and the elements from u2 get mapped to 2, and u is just the union of these two things. And then we could still get a function. So we have, so this is f1 and this is f2. So we could still get a function that agrees with these f1 and f2, but it wouldn't be constant anymore. So we can't glue it together and still get a constant functions. So that's what I meant by this. Okay, that's it for today. Next time we'll talk a little bit more about sheaves, some more properties and things we might need later, and then at some point we'll go on to define the structure sheaf and define what a affine scheme and what a scheme is. Okay, thanks for watching, have a good day, and bye.